So in a nutshell, here's the mathematical relationships between the semi-major axis, semi-minor axis, the distance from the center to the focal point, and the eccentricity of an ellipse. You'll see that the relationship between A, B, and F is the same as a right triangle with legs of side B and F and its long side of A. And then you can see that A is kind of the long part of the ellipse, and B is the short part of the ellipse. The eccentricity is defined by the ratio of the focal distance divided by the semi-major axis. So it can get really close to 1 before this thing slips down to being a line. And anything close to 0, probably 0, 0.1, 0.2, 0.3, 0.4, you barely even be able to tell the difference between that and a circle. Kepler's first law, this is from Wikipedia, is that the orbit of every planet is an ellipse with the Sun at one of its two foci. So here you can see an ellipse, and you can see there's this other focus right here, but basically if I were to connect a string between, wait, how come it's not drawing? Now it's drawing. If I was to place a string in between there, those 2 points, and kind of pull a pencil around, that would be the shape it would make. They also give a function which gives us the radius as a function of theta here. I'm going to snag that into Mathematica, and r of theta is a function of p divided by 1 plus, where'd my cursor go? 1 plus epsilon. It's a different epsilon. Let's put var epsilon. Var epsilon? No, doesn't recognize that term. Epsilon, just use that, times cosine of theta. Okay, that's going to take too long to show you every step of that, but let's set theta to be equal to, no, not theta, that's a variable. Set p equal to 1 and epsilon equal to 0.9, and the way I'm going to graph this is with a parametric plot, and I'm going to use of r cosine of theta and comma r sine of theta. And of course r is a function of theta, so I got to make sure that's in there, and we put theta going from 0 to 2 pi, and this is what we get. Now this kind of shows us that the focal point is right here, where the axis meets. Let's look at what this looks like with an eccentricity of 0.5. And now with an eccentricity of 0.5, it's hardly distinguishable from a circle. A little search on the web to find out what the eccentricity of the Earth's orbit is. It says less than 0.02. So let's go ahead and see what the eccentricity of 0.02 looks like. 0.02. Whoops. And what do we get? We get pretty much what looks like a perfect circle. So that's Kepler's first law, that the orbit of every planet is an ellipse, with the Sun at one of the foci. So let's move on to Kepler's second law of motion. You can see this video kind of shows it. as the planet orbits the sun, it sweeps out a small triangle so that basically it sweeps out equal areas in equal time. So in this video it says the same blue area is swept out in a given time. The green arrow going around this way, the green arrow is velocity, the purple arrow is the acceleration, and the other two purple arrows are acceleration components parallel and perpendicular to the velocity. So you can see one of the central arrow, one of the arrows goes right through the center of that point there where the sun is. The other two can be split into something parallel to the green arrow and something perpendicular to the green arrow. When it's parallel to the green arrow, it is either accelerating it as it is here or decelerating it as it was there. Accelerating, decelerating, accelerating, decelerating. And the other component is just increasing its acceleration toward the center and decreasing the acceleration towards the center. So Kepler's second law is a line joining a planet and the sun sweeps out equal areas during equal intervals of time. Okay, while I paused the video, I thought I could maybe try to use some of the math that they gave us in Wikipedia and try to come up with a sort of an equation that I could plug into Mathematica and make it animate the make it kind of use some of the data and animate the orbit using Kepler's second law. Unfortunately, right now it looks like, though I can kind of tell you what I did, but I didn't quite finish. Started getting a little bit complicated. I basically took this formula and solved it for d theta dt, and then I plugged in the value they gave for n, which was 2 pi over p. Changed the p to a t for period. Then I found I used the earlier formula for r as a function of theta, so I plugged that. So I plugged this. Replace r squared with p squared over 1 plus epsilon cosine theta squared. Actually, now that I look at it, I do have, looks like I made an error right there, in fact, because I squared just part of it, and I should have squared the whole thing. So I'll write that if you happen to look at the notes. And then, what else did I do? I put it in the form of a differential equation, basically separating the variables, getting all the thetas on one side and getting all the dt's on the other side. And then I went into, since I didn't have any idea how to integrate this thing, I plugged it into Mathematica, tried to integrate this. As a matter of fact, this should be, that is just 1 over, should be 1 plus epsilon cosine theta squared. Let's see how it integrates that. Well, that certainly didn't simplify anything, did it? In any case, at the end I was hoping to have some function, just a function theta of t, that would give me the angle at which, the angle measurement as it moved around in the elliptical fashion, going over around the sun fast and slowing down, and around the sun fast, slowing down, and then around the sun fast and slowing down. But for now I'm a little bit stumped, so let's move on to Kepler's third law. And Kepler's third law is an equation that is fairly simple to use, and basically looks like this. If it goes mp squared equals a cubed. Here's the expression of the third law as given in Wikipedia. The square of the orbital period, that's this p squared, is directly proportional to the cube of the semi-major axis of its orbit. That's the cube of the semi-major axis. So I've thrown in this m here, which is basically m if m for the Sun is 1 solar mass, and for the Earth-Sun system, A is equal to 1 astronomical unit, which is the distance between the Sun and the Earth, and P is equal to 1 year. And so that, if you use solar masses, astronomical units, and years, then this equation comes out this simple. But let's say I want the distance and the year of Venus. So if I look that up if I Google distance of Venus from Sun in AU, you can see here it says Venus orbits the Sun at an average distance of about 0.72 AU. So if I plug that into our equation, mp squared equals a cubed, then we can find out, if I plug in 0.72 cubed here, and m is 1, so we'll have p squared equals 0.72 cubed, or p is equal to the square root of 0.72 cubed, which comes out to be what? Well, there's a couple of ways you could enter that. 0.72 to the power of 3 over 2, 3 halves. That's to the power of 3 and the square root. Here's the square root of 0.72 cubed. Either way, you get 0.61, about 0.611 years. Now we can look up the length of a Venus year, and you'll see that it takes about here it says 224.7 days, or 62% of the time it takes Earth to complete an orbit around the Sun. 62% versus, what did I get? 0.611. So it's about this. It's a pretty good approximation, at least. And you'll find that relationship holds pretty well for all of the planets in the solar system.